I would like to come back to the notion of this local information. Now, since we have talked about gradients and Hessians, so by local information, we will mean to say the value of the function at given point and also the gradient and the Hessian. So as we described earlier, if you know the gradient, then you know sort of what might be a good direction to move in, and then we can try going there and reach a better point. Using this local information, what can we get in our quest for optimality? So I'm going to draw a picture and give you a motivation. So imagine again a function in one variable, just x1, and this vertical axis is plotting the values of the function fx1, and suppose my function has a shape like this. Some flat region, and then some steep falls. So suppose so we'll look at a few points of interest. So let us look at the point here, and the function value here is sort of a minimum if I look in a small neighborhood of this point. So this idea of neighborhood is quite important again. So if I can draw a circle around this point, in one dimension I can't really draw circles, but I can look at an interval. If I can take an interval around x1, a small interval, whatever arbitrary small size but finite size I can think of, if I look at that interval, that is a neighborhood of this point, and in this small neighborhood, clearly this point is having a nice value, much smaller than other points in this interval. So we say that this is a local minimum. So similarly, these 2 points are locally maximum, because if I take a small neighborhood around this point, then this is the value which is sort of the highest. So formally, local minimum is defined over a neighborhood, and says that there are no other better points in the neighborhood. So if I look at a point here on this plateau where the function is constant, and look at this interval around this point, then this point is actually both a local minimum and local maximum, because in this neighborhood there are no other better points. There is no other point which has a value lower than the value at this point. So this is locally minimum. Also it is locally maximum because in this interval there are no other better points having better or more value than this point. So this point is both a local minimum and a local maximum. If I look at the whole function on the x1 axis and try to find out the best possible minimum value, that is sometimes called global minimum, and this is far more difficult to find than a local minimum point, because I need to explore the full shape of the function, either using some analysis or through some brute force search. So we'll come to this global optimization or global minimization towards the end of this course. For the vast majority of this course, we will be interested in finding these locally minimum or locally maximum points, mostly relying on this local information. So this local information buys us access to these locally minimum or locally maximum points. But for this local information to be available, we need for useful local information, we will assume f is continuous and the first derivative or the gradient is also continuous. And for some results we might have to assume that the second derivative or the Hessian is also continuous. So that means f is a nice smooth twice differentiable function, and then we can safely rely on the information given by the derivatives and try to move in good directions and find points which are good in some neighborhood. So we will start looking at some of the mathematics behind this local information and try to come up with some first algorithms which help us in identifying these local minimum and local maximum points. So with this I'm going to stop and we will continue in the next lecture.